The work I will present today was actually initiated at my time at ETH Zurich and EMPA. And there we were faced with a problem. The problem was, well, actually what we want to do is to make simulations, flow fields, of realistic case studies and with realistic physics in there. If you want examples, it's very easy. You go to the website of the host of tonight and you find quite a lot of nice examples. We spoke a lot about uncertainties this morning. So if you want to have confidence in the results that you obtain, well, what you actually want to do is to do these studies, but you want to do them many times. You want to assess what is the uncertainty on the input parameters, what are the uncertainties or the everything related to initial and boundary conditions that usually they change over time and place. So you have a bit of a problem because all of those studies, they take quite a lot of computational resources. So what this problem is typical for the field of fluid dynamics, but it's also encountered in other fields. And there they found a solution, or a solution. It's called emulators. And so today I will speak about model emulation, and I hope to be able to convince you that this is at least a road to tackle this issue. So what is it actually? Well, you take your model that you're familiar with. For many of us, that's a CFD model. You give it some inputs, 5 meters per second wind coming from the north, and you get some output, which is a flow field. In an emulator, what you're going to do is try to find a relation between the input that you found and the output. And that's a stochastic relationship. And as soon as you have that relationship, and if that relationship is sufficiently simple, then you can use that relationship to do predictions instead of the model. Now, I know that relying on statistics is a bit awkward. So I'll guide you through based on an example. So we took something a bit more modest than the examples I showed you. This is an idealized city center, let's say, and we're interested in getting the wind speeds at pedestrian height, but that throughout an entire year based on a climate file with 10-minute data points. So even with a run simulation, this would take a tremendously long time. What's the first thing you do? Well, you say, how many runs can I afford? For my laptop, that would be 8 simulation runs. It's not so many, but okay. That would be 80 minutes, so it's not really a lot. Anyway, and then the variables that are considered here is the wind speed and the wind direction, and between which bounds, if I look at this climate file, well, I have double symmetry, so that's luck, so I can go between 0 and 90 degrees, wind speeds between 0 and 5 meters per second. Okay, that's my bounds, and I define for which combinations I'm going to do simulations. There are fancy techniques to do that. I just took a regular way of subdividing that. So 4 different wind directions, 2 different wind speeds. Then you do business as usual, meaning you make a mesh, you decide on your domain size, you decide on which model you will use, and so on and so on. You run your simulations, you end up with some results. Those results are the 3-dimensional wind field, pressure field, and everything you simulated, temperatures, moisture, whatever. It's a lot of data. For my application, I'm only interested in a subset of that. That is, the wind speeds at pedestrian height in the central region of my street canyon, and I don't need all these very refined meshes near the boundaries or all those things. I don't need it. 1 meter resolution is good enough for my purpose. So I downsample these data to have only what I need. And then I'm doing some pre-processing. First of all, I take my inputs and I scale them all to an interval between 0 and 1. Why? Well, wind directions are between 0 and 360 degrees, but I could also have taken radians, so then it would be between 0 and 2 pi. Well, I don't want the different orders of magnitude because I take different units that they affect my results. So therefore, I perform a normalization. I also do standardization of the output this time. I'm going to use stochastic models. Stochastic models, like they employ distributions, and as we will see, it's beneficial if you know something about this distribution. So I will scale my data such that the mean is 0 and the standard deviation is 1. You can do that with any data set. I don't assume a certain shape of this distribution. I just say mean 0, standard deviation 1. And the final thing, I will reduce the data, do some compression. I already did a selection, that is already a reduction, but here I will go a step further. For example, you do a principal component analysis or a POD, as some of you might call it. You take only the first number of modes, and that's the modes you preserve. Okay, then you have basically two options. We have inputs, we have outputs, we need to relate them. If you have only one input, one output, it's pretty simple. You say, well, okay, I see these data points, I fit a curve through it. Okay, but what if it's a full wind field? What if it's n-dimensional? Fitting a curve becomes pretty complex, and that's when stochastic processes come in. What is a stochastic process? It's basically all possible functions. The space of all possible functions, and every function gets a probability assigned to it. That probability is 0 if it's a function that absolutely does not fit your data set. Will be very high when it fits your data set pretty nicely. But so if the data changes, the function that will be taken will also be a different one. We will use stochastic processes. There are a number of variables in them. They don't call them variables, they call them hyperparameters. Okay. We're almost there. One more major ingredient, that's prior information. You can include some subjective prior information. It's things that you know. For example, my data, I did some pre-processing. I know that it has a mean 0 and a standard deviation of 1. Something that I know, I can use this when I'm going to make predictions. I also know I truncated because I did a POD analysis, I threw away some data, so I have a truncation error. The mean of that truncation error should be 0. The magnitude should be limited. There are other things, periodicity, for example, some bounds if you do concentrations. Well, they cannot be negative, except when you do measurements and you didn't calibrate well, but okay, that's another thing. Good. And then the key point is basically relating these two. Prior information, for example, your truncation errors, mean 0, standard deviation not too large. That's what you think it is. But you also have your data set, and your data set that tells you, well, probably you are better off with predicting with a mean of, I don't know, 2 and a standard deviation like that. What an emulator will do is try to take a compromise between these two. It will give you a posterior. That posterior is a balanced evaluation of the prior and the likelihood. So these two are in there, and depending on the strength of them. So if you have a lot of data points, the likelihood will prevail. If you don't have a lot, then it will be the prior. Okay, that sounds all a bit fuzzy. I know it's, first of all, statistics, and secondly, there is a subjective element, so I know we have to be pretty careful in assessing this. So, first test. Qualitative information. On the left, simulated wind field. On the right, emulated wind field. If you take a difference image, you will see there is some difference between the two, but it's basically noise. The main difference between them you don't see, but that's the time. Figure on the left took 80 hours to simulate. Figure on the right took something like 80 microseconds on a normal laptop. So, if you're happy with these differences, which are very small, then probably you will like the time it took to do this. But okay, it's just one pretty image. We have to go a bit more in depth. First of all, focus on the picture on the left. These are 48,000 image points. Horizontal axis, simulated data. Vertical axis, emulated data for 4 different wind speeds, for 2 different wind speeds, 4 different angles, and you notice that everything basically correlates. You also notice it's not a perfect line, that's the truncation error. It's our data compression that is in there. So this is basically reproducing the data that I put into the model, or into the method. And as you can see, we can do that. But our idea is to start predicting with something like this. That's here on the right. That's predictions. I did also a simulation for 2 different wind directions and 2 different wind speeds that are not like a nice mean between two other results, but something else. And you see simulations versus predictions. Again, we have a pretty good comparison, but less good than the initial data. Are we happy with this? Well, depends on you, basically. 82% of these data are within a factor 2. And the biggest errors are basically the non-zero data values, or their very small wind speeds, so the wakes of buildings. There you actually make a relative error, which is the largest. It's pretty logic, actually. If you look at some common metrics, fractional bias, 10 to the power minus 2. There are not many guidelines, but some guidelines say you should be below 1.5. Well, we're a factor 100 below, so that's actually not too bad. Normalized mean square errors, again, not many guidelines. If you cite one, they say, well, below 0.3, we're a factor 10 to the power 5 lower. So for the criteria that are used to evaluate models, you would say this is excellent. But the nice thing is that actually it can be better, because we made some assumptions. And now let's look at these assumptions one by one. First of all, if you want more accuracy, what can you do? Well, just instead of 8 simulations, take 14, for example. If you can afford 6 more simulation runs, so instead of every 30-degree angle, you do every 15-degree angle, you notice, well, top figure is for the training data that are represented nicely in any case. Bottom figure is for our predictions, and it's the predictions that we want to improve. And what you see is normalized mean square error and fractional bias, they decrease. And the blue line, the fact2, so the number of predictions within a factor 2, that one increases quite dramatically to actually the same point as our training data set. Or otherwise, other words to say the same thing, we now have predictions that are in the same level of accuracy as our training data set, meaning the 45-degree line. Okay, other thing, we did some compression. Compression is not good, and that's what you see here. It's the number of basis functions, so basically the number of modes we include. More modes you include means less compression. Less compression corresponds to more accurate data. Lower errors, higher accuracy. Logical, you also see it levels off. So you can, only 4 modes in this case is good. The 5th mode, very small increase in accuracy. 6th mode, 7th, 8th, you don't add anything anymore. Next thing, the subjective information. Subjective, the prior distribution. So what is my belief about the data? And I took some possible beliefs you see here on the right. So you have very narrow distributions, very wide distributions, very symmetric distributions or asymmetric distributions, even linear ones, and very small emphasis on one single value. On the left, you see the result this has on my predictions. General message, no effect. Why not? Because I'm sitting here on 48,000 data points of a UVZ component, so 150,000 points of data. That's a data set that is large enough to draw some statistics from. So it's the data that prevails here, and whatever I say, well, the truncation error is probably around that value. It doesn't matter. It takes everything from the data. If I would have only 10 data points, 100 data points, then this would have a dramatic impact on my results. But for us, CFD, wind tunnel, PIV data, you're usually in a case where the data is sufficiently strong to outrule everything that is subjective. So you're dealing only with the objective thing here. So an objective method which is fast and has controllable accuracy. It's actually what you would like to have. So now back to the initial problem. We wanted to have our climate file and run the simulations. The black line, top figure, gives you the wind speed, at the meteo station. Bottom gives you the wind direction, and the colored lines are at different locations inside the urban area. What are the corresponding wind speeds and wind directions there? Simulation with CFD would take you quite a lot of time. Here, this is just a small piece of a very long time series. Took about something like 3 minutes in this case. Every point has an error bar associated with it, which I didn't plot here, just not to overload the graph. But for every point, you also know what is the uncertainty associated with that prediction. And obviously the errors, we verified that the errors are within the uncertainty that is given, so within the 2 sigma. Once you know this, you can go a step further and you say, well, okay, the local wind field, that one defines the local energy losses of buildings. So at different locations on the facade of a building, I can calculate the local energy losses based on my local wind fields. And you see for cooling, that is about, well, on the average, it's about 2% that you have a different prediction with including that local effect or not including that local effect. And for heating, it's, let's say, between 0 and 6, so it's here a 4% approximate, 4% average. So you see, you can include these things, overhead time here, extra time needed for a simulation over a full year, something like 30 minutes to include the microclimate. So I arrived to my conclusions, and that is that I propose here to start using emulators. And the main advantage is really that they're extremely fast. That's their main advantage. They're not accurate, but they have controllable accuracy. Meaning, if you have a larger data set that you use to train them, they get more accurate. If you use less compression, they get more accurate, and that accuracy at least is quantifiable and you can know it ahead of time. And it's not restricted to CFD models. It's basically whatever data you have. Can also be measurement data, does not need to be simulations. Nevertheless, I make a case here for emulators, but I'm not saying that emulators can ever replace simulators. That's absolutely not the point. They only come at help to do things that are prohibitively expensive when you want to do a simulation. So emulators, many runs of something with a restricted set of input parameters, simulators for all the rest is actually where physics matter. So I have a list of things where emulators can play a role, but we're almost at the deadline. So I thank you for your attention.